Okay, so how do we do it? How do we build a penalty? And the idea is as follows. So let's consider we have two nodes which represent two devices. So we have a node I and a node I prime. These are two devices, let's say my smartphone and my friend's smartphone or my neighbor's smartphone. And the neighbor and me, we collect our own data, like activity logs from our exercises. So each of us collects data, and then each of us wants to train a model, a fitness advisor app, let's say, but we somehow want to agree it on a few certain things. So I know, for example, that my neighbor is similar to me and that we don't like to do running when it rains. And this kind of agreement we can implement by forcing the trained models. So I have a trained model here for me, for I and node I, and the trained model, this red curve for node I prime, to agree on a test set. And this test set could be carefully selected reference days. So like specific days in the past where there were specific weather conditions and where we both agree what to do. Let's say there was one day where it was 35 degrees. So we both decided to go swimming. And this we can enforce by making this discrepancy of these two hypotheses on the test set small. That's the main idea behind all the methods that we will learn in this course. But we can use different ways to measure the discrepancy, like the loss function for machine learning methods. Also, the discrepancy measure here, how you measure this discrepancy in detail is a design choice. And one of these design choices is the squared error loss. So we can compare the predictions of these two models on a test set. This gives us predicted values, or let's call them pseudo labels, and we compute the squared error loss between those two. And this gives us a measure for the disagreement of the trained model at node I and node I prime. What else could we use to measure the discrepancy? Well, if these models are not regression models, so they don't deliver numeric quantities, but they deliver labels or categories, then the squared error loss is typically not a good choice, and we could use something like the cross entropy. So whatever you know from basic machine learning methods as possible loss function, you could also use for this discrepancy measure. Yeah, I would like to point out that this test set on which we compare those two models, this can be different for different edges. So this test set is tailored to a pair of nodes. So this test set is only used for node I and I prime, and for another pair of nodes, for another edge in our federated learning graph, federated learning network, we might use another test set. So we can tailor this test set to the edges in the network. And also this test set in some sense is a design choice. That, for example, you can try out in your federated learning project, you can try out different constructions of these test sets. Does any one of you have some intuition or some idea how to build such a test set between two nodes in a federated learning network? So let's say you have two nodes. Let's say this is one node, and this one node carries a local data set. And then this other node carries another local data set, like these red dots here. So how could you build a test set that somehow compares those two nodes? What would be a natural choice, or what would be your intuition? Yeah, let's assume they can communicate, so they can arrange whatever they want. The overlap. So yeah, so this test set could be built from subsets of these local data sets. So for example, you could say, I built this test set by randomly selecting 10% of this data set and randomly selecting 10% of that data set and put them together into a test set. Or you could say you pick those data points from this data set that have very close neighbors in that data set. So in some sense, they overlap. Another option could be, let's say these local data sets are for a classification problem where you want to classify each data point here, each dot is an image, and you want to classify it into cat and dog. And similar here. So here you also have a cat dog classification data set. And then you could say you construct this test set by randomly generating cat images and dog images. So this is something that can be very specific for your application. How you construct this test data set. Okay, any questions at this point? That was a good question. Why is the third way the focus of this course? So why do I focus on this penalty term perspective? And that's a very good question. I mean, the first answer is because it's close to my current research. So I know the most about this about this approach, but I don't dare to say that this is the best way to do it. And I welcome you to, for example, in the paper review, pick a paper that uses a different approach, let's say using somehow data augmentation in a privacy-friendly way. And you are very welcome in your paper review to then contrast this approach with this penalty term approach in the course and tell what is better, what is worse. Okay. Yes. Yeah. Very good question. So the question is, how can we build a test set, or how can we construct this test set without leaking private information from the local test set? One naive way is that you somehow randomly generate one test set, and every pair of nodes uses it. So you completely randomly generate this test set. Another option could be you estimate somehow the distribution of the local data sets, and then from this estimate of the distribution, you draw random samples. This could be a way to generate this test set in a privacy-friendly way. Yeah, so sharing chunks or sharing 10% of the raw data points here might be not privacy-friendly. Very good point. Yeah, this was now also asked in the chat. Yeah. So this what I first mentioned, this simple idea of taking 10% of this data points, this data set, and 10% of this data set, and then combining it to make to produce a test set might be not privacy friendly. So instead, you could estimate the distribution of this data set and estimate the distribution of this data set, and then randomly sample realizations from these distributions. So this would be a more privacy-friendly way. Okay. There's one comment. Each node can send the final local weights to the other node, and the target node can calculate the loss of those weights over its subset of data and send it back. Yes. So you don't need to, yeah. So this is just a visualization of this construction process. I mean, you don't need to really share raw data. You only need to share predictions of this model, for example, of the red model on the test set, and sharing these predictions, only sharing these predictions might not be too much privacy unfriendly. Okay. But this is an already in very detailed discussion. So let me now move on and yeah, just point out that when you work out this for this simple case, this disagreement measure, and let's say we use linear models. So we use linear models at each of these two devices of these nodes. When we insert the formula for the linear model, we get the following expression for the disagreement. And this is quite nice because this expression is a generalized norm. So this is or a squared norm. If this in the middle, this matrix would be identity, then we would have here, we would have if this would be identity, then what we see here would be exactly the squared Euclidean norm. But instead of the squared Euclidean norm, we have here this matrix, which is some positive semi-definite matrix that defines a generalized squared norm.